Hello again and welcome back. We're going to continue our discussion on electrocyclizations, this time looking at systems with more than 3 atoms. So probably the main focus of today is going to be 5 atom species, looking at the 4 and 6 electron variants of those. We will also look at 6 atom species and 8 atom species as well, but not to the same extent. And just as a quick plug, if you haven't looked at the previous video, which looked at 3 atom electrocyclizations, I'd recommend doing that before watching this one, simply because it will cover a lot of the basics that I might gloss over here. So here's the arrangement of the pi orbitals that we would expect to see for a 5 atom species. We've got psi 1, 2 and 3. If we're focusing on a 4 electron species, we're going to be up here in psi 2. This is where our electrons are going to be populating, at least if we're dealing with a thermal system, which we will. So this gives us our arrangements of the orbitals, which we can place on our ring opened form with the corresponding cyclized form shown underneath. The second option would be the 6 electron anionic cyclopentane species. This takes us up to the psi 3 level, as we can only fit 2 electrons in each one of these orbital configurations. If we transpose this arrangement of orbitals onto the ring opened form of our cyclopentane, that gives us this arrangement shown here, and comparing the orientation of the pi orbitals at this terminal position, we can see that it is opposite to the terminal orientations for the 4 electron species. This means if we're going to rotate these terminal pi orbitals, we're going to have to rotate them in a different way to bring matching lobes of the orbitals together to form the bond. This also translates to a different orientation of the R groups once the cyclization forms between the 4 electron species and the 6 electron species. Now, to begin with, we're going to talk about the 4 electron species, so cationic cyclopentanes. Just to point it out, we've got a delocalized positive charge over these 3 pi orbitals. There is also a double bond delocalized around these 3 atoms here. Because it's a 4 electron system, to either ring open it or ring close it, you're going to have to rotate the terminal pi orbitals in a con-rotatory fashion. If we quickly look at the orientation of these p orbitals here, we can see that they have opposite orientation to one another at this terminal position shown here. There are 3 inset images showing how the bonding orbitals change and rotate across the course of the reaction. In all cases, we're going to be viewing both molecules from this orientation. So for our cyclized species, looking at it in this orientation gives us this representation of the bond that we are going to break across the reaction. Because this is a 4 electron system, we need to rotate it in a con-rotatory fashion, which means each of these terminal carbons and their pi orbitals need to rotate in the same way, either both clockwise or both counterclockwise. Looking at the arrangement of the R groups, if we were to rotate both of these clockwise, they're going to move inwards towards one another. And this is going to create steric issues. So instead, I'm showing the con-rotatory process as being counterclockwise. This moves both of these R groups outwards, giving our ring-opened form shown here. And if we have a look at the arrangement of the p orbitals on these terminal carbons, it matches nicely with what we expect to see for a 5 atom 4 electron species. Now doing exactly the same thing for an anionic cyclopentane, shown over here. Once more, we've got a delocalized negative charge over these 3 atoms. There is also a delocalized double bond across these 3 positions. Because we're dealing with 6 electrons, it's 4n plus 2, which means we have to proceed with a disrotatory mechanism. I've shown that here by rotating both of the R groups outwards, which is the logical choice, seeing as if you rotate them inwards, they are going to sterically clash with one another. That makes this disrotatory approach favoured. However, if the R groups were linked together in some kind of cyclic structure, the only valid way to perform this disrotation would be to rotate them towards one another, so the R groups going inwards. But assuming they're not linked together, this outward rotation is going to be favoured. Just to highlight the Woodward-Hoffmann rules that I've just used to assign the con-rotatory or disrotatory mechanisms. Here we're dealing with 1, 2, 3, 4, 5 atoms, which will have 5 electrons, but subtracting 1 for the positive charge. So a 4 electron pi system that places it within the 4n pi electron category where n is equal to 1. So assuming it's a thermal process, it's going to be a con-rotatory mechanism. But if we're dealing with the anionic version of a 5 atom pi system, now we're dealing with 1, 2, 3, 4, 5, 6 electrons in our pi system. That categorises it as a 4n plus 2, whereby n is equal to 1. And under thermal conditions, that means that that process has to proceed by a disrotatory ring cyclization mechanism. We'll go over a quick example whereby this chemistry is used, specifically the Nazarov reaction shown here. It starts with this divinilic ketone, which initially gets protonated, shifting electron density out of this 5-atom open form structure. We can clearly see our 1, 2, 3, 4, 5 atoms, 1, 2, 3, 4 electrons within it. From the Woodward-Hoffmann rules, we can assign this as a con-rotatory electrocyclization reaction, and I've shown the transition state here for closing the ring. As you can see, we've got 2 pi orbitals that are in opposite alignment, and we're going to rotate them both clockwise, bringing these 2 green orbitals together to form this new bond. Now, because we're rotating these carbons both in a clockwise fashion, this R group is going to move upwards, this R group is going to move downwards, and that gives this stereochemical arrangement shown here in the product. When the proton departs, the electron density can move back, reforming this ketone with an adjacent double bond. You'll note that the stereochemistry is locked in for one of these R groups when the reaction has concluded. It's also worth noting that we've started the reaction here, concluded it over here. However, the reaction could equally proceed in reverse, meaning we could take this cyclized system, we could rotate our carbons counterclockwise, breaking apart this bond, and then arriving back at our starting materials over here. Here's a nice example from Wikipedia. It shows a Nazarov cyclization which then cascades to give you multiple functional groups with well-defined diastereoselectivity. So our starting material would be a ketone. Looks like some sort of weird variant of squalene. First step is a Lewis acid coordinates to the ketone, drawing out the electron density and forming this 5-atom, 4-electron cationic system, which undergoes cyclization in a con-rotatory manner. Interestingly, the stereochemistry of this R group places this long chain beneath the newly formed carbocation. So when electron density from this double bond attacks the carbocation, this methyl group is going to be situated above this long alkyl chain, implementing diastereoselectivity here. Now the carbocation has moved further down the molecule. There is electron density within this aromatic ring. It is situated beneath the carbocation. So once more you get attack from underneath, placing this methyl group above the aromatic backbone. So from this Nazarov cyclization, we get 1, 2, 3, arguably 4 chiral centers forming with excellent stereo control. We'll briefly touch on 8 atom species involving 8 electrons. This will be a psi-4 system with alternating pairs of pi orbitals, giving us this alternating double bond system. Per the Woodward-Hoffmann rules, closure of this ring should be con-rotatory, which would give us this structure shown down here. I also dug out a research article which showed a 3-dimensional representation of the transition state, where you can see that these pi orbitals are really nicely stacked on top of one another. So these types of species are primed to undergo cyclizations. And starting with our 8-atom, 8-electron ring-opened form, we can undergo electrocyclization, thermal conditions, con-rotatory mechanism of closure, giving this arrangement of the methyl groups here. But interestingly, if we look at this product, we can view it as a 1, 2, 3, 4, 5, 6-atom, 6-electron species of its own, meaning that it too could undergo electrocyclization. And per the Woodward-Hoffmann rules, 6 atoms, 6 electrons, it's going to undergo a disrotatory electrocyclic ring closure under thermal conditions, giving us either of these 2 products shown here. I suppose arguably you consider these as now 1, 2, 3, 4 atom, 4 electron species that could themselves undergo electrocyclization. However, this is probably not going to be thermodynamically favoured, as with each cyclization you're building up strain within the molecule. Then again, if you go from thermal to photochemical means of reacting these molecules, maybe you could form the tricyclic products. So that's all I really have to say about greater than 3 atom electrocyclizations. Once more, with good understanding of frontier molecular orbital theory, prediction of conrotatory and disrotatory motion of the terminal atoms allows you to predict and understand diastereoselective trends that you'll see in the products. These larger atom electrocyclizations can occur in a cascading fashion, recognising that the number of pi bonds or pi orbitals decreases with each step. With what we've covered, you should be able to extrapolate to other atom and electron combinations, predicting whether or not it's disrotatory or conrotatory and what the arrangement of the functional groups in the products should be. That's all I have for today. Thanks for watching.